So hi there, the course is still optics, and here I will be giving my first lecture on our chapter 6, and of course chapter 6 will be focusing on propagation effects that we will have when one light is propagating in different kinds of media. So essentially I will first just go through the table of contents regarding this chapter, and then I will start with my actual main thing regarding 6.1, but don't worry, the actual lecture will be short, so I will just speak about 5 minutes giving you an introduction for the whole chapter and then maybe a few minutes regarding the actual lecture. So in short, the motivation behind this chapter and what we will be covering here is that I will start by giving you a brief motivation into understanding of propagation. So I will introduce a little bit about the terminology along the way. So I will mainly speak about reflection and refraction as processes of interest. And these are the main processes of interest here. And I will introduce to you the laws of reflection and refraction. So essentially that would be the Snell's law. And I will revisit the concept of an optical path length, or OPL for short. And those will be the kind of laws, equations, and concepts that we can use quite a lot and will be used extensively in the subsequent follow-up chapters, especially in the final ones where we are dealing with geometrical optics and we are wanting to understand how lenses behave and how images get formed in normal optical instrumentation and so forth. Then, in 6.3 lecture, I will be speaking about the electromagnetic theory of reflection and refraction, and what that means is that essentially I will derive the Snell's law and the law of reflection by using Maxwell's equations as the starting point. So we will see there that there are boundary conditions arising from the Maxwell's equations when we apply them to a given type of an interface. And these boundary conditions, essentially they give us continuity equations for field components, and those continuity equations then give rise to Snell's law. So that would be the law of refraction and then the law of reflection. So that's a nice lecture, I think, because then we are really putting things into a firm grounding so that we see ourselves, everything is really based on the Maxwell's equations. Then in 6.4, in a way, that would be the follow-up from 6.3, and there I will be introducing to you the Fresnel coefficients. And essentially Fresnel coefficients are the coefficients numbers that tell us quantitatively how much of light is being reflected or refracted at an interface. And those will be introduced, or I would say maybe a better word would be that they will be derived for two main polarization components. Again, essentially applying boundary conditions or continuity equations arising from the Maxwell's equations. And then I think I will also introduce a Brewster's angle as a specific condition where something interesting happens in terms of reflection and refraction, and that actually has quite a bit of importance in terms of applications. And then in 6.5, I will generalize the treatment based on Fresnel's coefficients. So those would be the coefficients that we use when we are dealing with fields. And now we generalize the treatment into irradiances. So there we will introduce parameters such as reflectivity and transmissivity, and they essentially describe in a quantitative manner how light is being reflected / refracted at an interface. And there we are now using terms of irradiances so that we really can quantitatively calculate how much of light goes through and how much of light is being transmitted through an interface. And then finally, in 6.6, regarding total internal reflection, I will introduce to you a phenomena of total internal reflection and frustrated total internal reflection. And I will speak a little bit of the evanescent fields along the way, and I will try my best of elucidating how these phenomena can actually be used in practical applications and actually how they are being used in applications. And there is spoiler alert, I guess I would already say that I should say that the waveguides and fibers, of course, would be the components of interest when we are thinking about total internal reflection. Just to mention one specific broad range of applications. So this is what I will be speaking here in general in chapter 6, and now I will be starting my actual first lecture regarding the wavefronts and rays. And here I will just start by just giving a brief classification of what kind of treatment we will be using in this chapter. So we can understand propagation of light using two different kinds of treatments, or broadly speaking, we can understand propagation of light using two different treatments. So one picture, and this will be extensively used in the final chapter on geometrical optics. In one description, we think of light as a bunch of rays, light rays, and there it is these light rays that give us a direction along which the energy of light is being propagating. And these essentially are orthogonal with respect to a specific local wavefront, and these will be more treated during the chapter 10. So this is like a picture trying to highlight what these rays of light are. So we can understand that we have some kind of propagating electromagnetic field here with this curly wave here, and the black curly wave here describes that it is the wavefront. So in this wavefront, the phase is a constant valued quantity, and then subsequently we are imagining that how this kind of wavefront actually is being propagating in space is that we can imagine that we have these kind of tiny rays of light that propagates straight ahead, and then the direction of these rays of light will be defined as being normal with respect to the local wavefront here. So this is the one picture of thinking of propagation of light. And if you're familiar with the Fourier transforms, then maybe I should already warn you here that the rays of light, essentially we can understand them as a kind of Fourier transformation of our field from real space x, y, z variables into spatial frequencies, so kx, ky, and kz variables. Most of the time just kx and ky. And there, each of these spatial frequency components correspond to a plane wave propagating in a given direction. And look and behold here, these guys, these rays of light, they kind of look like a plane waves propagating in a given direction. So in a way, we can equate most of the time that each of these rays, they correspond to different spatial frequencies associated with the electric field distribution. So in a way, let me try to say things in a nutshell. So we start with the wavefront description. So that would be our electric field E as a function of normal spatial coordinates x, y, and z. And now we just mindlessly Fourier transform this quantity. We can always change the basis of a function. And now I'm describing my electric field E in the spatial domain. So now I have my variables kx and ky and kz. And now what these different components now mean is that we are essentially like looking at plane waves propagating in a specific direction. So that would be the kind of a mathematical connection that we could make. But in this introductory course, we cannot assume that you are very familiar with the concepts of Fourier transforms. So I guess we kind of be a little bit ambiguous about it and don't utilize these mathematics too much. But I just wanted to say that it's out there in case you're interested. And the second way of looking at things would be the field and looking at fields in terms of their wavefronts. And the wavefront, this is a really important quantity to understand. Wavefront is being defined as a surface where the phase of the wave is constant. So that black curly line in that schematic figure. And this wavefront, of course, it propagates at the speed of light in that given medium. So here c divided with n, depending on the refractive index profile of the material. And here the wave vector k is perpendicular to the local portion of the wavefront. So this is how we can understand things. And broadly speaking, these are the two different kinds of ways of trying to understand what is a field and how it propagates. And in a way, they can even be thought of as being the kind of conjugate planes. So in the wavefront picture, we are looking at the field in terms of x, y, and z coordinates. And in the ray description, we're looking at things more in the Fourier domain, so in terms of spatial frequencies kx, ky, and kz. So this is what I wanted to say on this lecture. So I hope this was a good introduction to what we will be unraveling in the next lectures, and please join me quickly when we are actually starting the whole main thing, and we will be looking more into the details how light can be reflected and being refracted at interfaces. So how light propagates nearby these interfaces. So I thank you for your patience and spending your time with me. Thanks and bye-bye.